All right, so now I'm going to spend a brief amount of time talking a little bit about some exceptions that don't totally fall into this aereo category of assessing the relative stability of conjugate bases. Okay, so now because they are so similar, aereo cannot be used to explain the difference in pKs between two compounds such as ethanol and terbutanol that we see here. Okay, you can see that they both have the hydrogen attached to an oxygen. There's no resonance. There's no inductive effects. What's going on? Why is ethanol 2 orders of magnitude more acidic than terbutanol? Okay. As with all acids, the difference in acidity is due to the relative stability of their conjugate bases. Okay, the ability of the solvent to stabilize the conjugate bases comes into play for this example. Okay, the solvent, again, remember, when we're assessing the values, pKa values, and when we're talking about stability of acids, we're looking in water. Okay, strong acid, how much does it dissolve in water? Okay, so the solvent plays a role here. The solvent must form ion dipole attractions to stabilize the formal negative charge that appears on the conjugate base when either one of our two acids we're looking at loses their proton. If the terbutoxide is sterically hindered, as we can see that it is, it's got big groups attached to it, it won't be as well solvated as the ethoxide anion that is formed. And that's why we see that terbutanol isn't as acidic as ethanol. Okay. I do want to mention that this is kind of like one of those rare exceptions. You will talk a little bit more about it in chapter 13 when you get to alcohols. But for right now, I'm just kind of showing it to you as an example of an exception. You don't need to be concerned about it, okay? Another thing I do want to mention is something called counterions, okay? Counterions are also known as spectator ions, and they're always present because they are needed to balance out the overall reaction of a solution, but sometimes they're not actually written out in a chemical reaction. Okay, so we actually cannot have bases just existing in nature as negatively charged compounds. They always exist with a positively charged cation as a salt form. Okay, sometimes that's shown, sometimes it's not shown. You can see here we have NaNH2 plus H2O goes to NH3 and NaOH. Sometimes it's shown like that. Sometimes it is not shown without that Na plus counterion. The counterion does nothing. It just sits there and exists to help balance out the charge. Okay. All right. Now, finally, we're going to talk a little bit, very little bit, about Lewis acids and Lewis bases. Okay, so the Lewis acid and Lewis base definition. A Lewis acid accepts a pair of electrons, and a Lewis base donates a pair of electrons. Okay, acids under that Bronsted-Lowry definition are also acids under the Lewis base definition, Lewis acid definition. Okay, and bases under the Bronsted-Lowry definition are also bases under the Lewis base definition. Okay, this fits reactions, both definitions. Okay, the Bronsted-Lowry are acids, whether you call them Bronsted-Lowry or Lewis acids. However, there are some Lewis acids and Lewis bases that do not fall into the Bronsted-Lowry category. Okay. Okay. Here, again, remembering that our Lewis acid accepts and shares a pair of electrons, we can see that our boron compound is going to be our Lewis acid, this guy right here, because he is accepting a pair of electrons from the oxygen. Now, that fits the Lewis definition, but it doesn't fit our Bronsted-Lowry definition, okay? The water molecule is donating and sharing its pair of electrons. And so it is now acting as a Lewis base. Okay, so as you can see, the Lewis acid and the Lewis base definition is quite different.